Hello all and welcome to the 35th Surface Ventures keynote webinar. You see some of you have done so already, but for the others, please can you say hello in the chat box and tell us where you're joining from today. It's like some great places there, Malta, Munich, Pakistan. Great to see we have such a wide and varied audience today. My name is Dr. Sam McMaster and I'm the event manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class material science education for both academia and industry. Today, it's my pleasure to introduce Dr. Matthias Voigt of Matrilab Materials Tribology Lubrication. Dr. Matthias Voigt is a managing partner of Matrilab with more than 37 years of experience in R&D of feasibility studies on disruptive technologies, relationships between CO2 and friction, sustainability and wear protection, environmentally accepted lubricants, cause root failure analysis, slip rolling alloys, fine ceramics, ceramic composites, thin film coatings, and thermally sprayed coatings, abrasive wear, as well as alternative lubricant formulations and tribotesting, including dissemination of all of the aforementioned into industrial applications. He has authored more than 380 publications, edited 12 books, and had 51 priority patents filed. Publications have generated more than 3,200 citations. Quite recently, he has been the recipient of the ASTM Eagle Award, an award of excellence, and is elected STLE Fellow, as chairman of the SRV Test Methods DIN Standard 51834, parts 1 to 7, 12 ASTM test methods, and ISO 19291, and is vice president of the German Society for Tribology. Many thanks to today's partner, Artec Instruments. We will have a short presentation from Philip Kemp later in the event. And we will also be releasing poll questions and handouts from Artec throughout the event. So I will alert you in the chat when those will be coming. As we go along, please type your questions into the chat and I will mark them for the Q&A session, which we'll do after both of today's presentations. We're planning to go for around 60 minutes today, and we'll be sharing a link for your attendance certificates later in the event. So I'll once again alert you in the chat for that. So without further ado, let's welcome our speaker to the stage. Please come on stage, Matthias. Fantastic. Bring your slides up. There you go.
So, ladies and gentlemen, a warm welcome also from my side to this topic, designing tribotests and electrifying tribometry. Not only powertrains are electrified, but in consequence also the tools we use needs to be electrified. The starting point is we have so many tribological test equipment flying around, test geometries, methodologies, that the question is why we need all these different test methodologies in order to characterize friction, wear, and load carrying capacity of lubricants and materials. The question is, the answer is quite easy, because we have such a large range of operating conditions, test geometries, and in order to have meaningful results and results you can transfer from a test equipment to the application, you need a lot of different testing machines to mimic those applications. What happened in the last, let's say, 70, 60 years, there are some test equipment which were standardized. And this means that this test equipment or these test methodologies have reached a certain penetration and also acceptance. If you go back into the history, you'll see that the first tribometer may be invented by Leonardo da Vinci, but the first tribometer where we can say you have a drive unit, you have something to measure temperature or forces, can be seen around 1850. So tribometry is a quite new discipline. Test equipment, tribometric test equipment, which is able to have a controlled drive unit and so on were seen around 1890, not before. The most and widely known test equipment is the Shell 4-ball machine, which was invented or designed at Shell in Rotterdam in the 30s and moved then to Germany. We have the SRV machine, which surfaced end of 60s, beginning of 70s. Pin on disc tribometer are quite old. Also, the Brugger lubricant tester FZG was also designed in the 30s in Germany. We have component tests like FE8 and FE9, rolling bearing, unfortunately only standardized here in Germany. Very important for hydraulic systems is the vane pump and also the coefficient of friction of automatic transmission fluids. These are key test equipment, all more or less developed here in Germany and have their origin in Germany. Why we now use test equipment? You can build a vehicle and test in a vehicle. This would be on top the category number 1, but this takes a lot of time. You need a full application and it's costly and time consuming. When you now have not an application, what you do, you are developing for a future application, a lubricant or a material or a coating, then you must have a bench test or even a tribometer. We have in Germany six levels or 6 categories. Category 1, 2, 3 are application-oriented tests or practices, and then we have tribometers or lab scale test equipment up to a small components, which are the categories 4 to 6. But what is now the consequence? On the right side, you see typical trends. When we start with the impact of design, so more and more you go into an application, the impact of design and manufacturing on the test results become more and more important. So when you want to test the behavior of a material, then the best way is to have the categories 4, 5, or 6, where the impact of the design is not so dominant. Another point is if you want to measure a lot of properties, it is easy to instrument a tribometer. To instrument a full application is of course possible, but time consuming and also expensive. The key issue about we have to talk today is also the transferability of results. It is logic. If you are far away from the application and you have the impact of design, the question comes up, how transferable are the test results in a tribometer later to the application? Also, it's clear if you have completely new materials, then it's impossible to test them in an applications because you are still unable to manufacture the pieces from these new materials, and you must go automatically into test category between 4 and 6. Also, very important to use a tribometer is that you have the cost issue. If you put a vehicle, a full vehicle, on a rolling test or rolling bench test, it's per hour extremely expensive. And if you make some tests in a tribometer, the costs for tests for the specimen are orders of magnitude lower. So you see here already there are pros and cons, and you must decide by yourself in which technology readiness level you are positioned in order to select the right level of categories for testing. As the impact of design increases from category 6 to 1, in the opposite way, the impact of a material is in the opposite direction. When you come from category 1 to 6, you see, especially in categories 5 and 6, the impact of the materials of a coating or of a lubricant. Same for the testing time. If you make engine tests or vehicle tests, you need thousands of hours. And in a tribometer, you can get after some hours meaningful test data about the functional behavior of a coating, a material, a lubricant, an additive, and also the interplay and the interaction between these. So what is a tribo system? The key point is that tribology or tribotesting is much more complex than analytical science. And the reason is that we measure a system property or we measure functional properties. Basically, friction and wear is everywhere in our life, in our industry. There is no industry where you do not have tribo system. A tribo system consists, a closed tribo system consists, as you see in the center, by two tribo elements. Tribo element 1 can be the primary part, and tribo element 2 can be the counterpart. And it is here, at least in Germany, defined in that way that the tribo element 1, the primary part, is the element who is continuously in contact with the counterpart, and surface element of the counterpart comes repeatedly into the contact. This means a bearing shell in a sliding bearing is tribo element 1, and the rotating shaft is tribo element 2, because the bearing shell continuously touches the shaft, and then surface element of the shaft comes periodically into contact. A similar situation you have for piston ring cylinder liners. The piston ring is the tribo element 1 because it is in contact with the cylinder liner the whole time, and the surface element of a cylinder liner comes repeatedly into the contact. Those contact situation, irrespective if you have sliding, rolling, low or high contact stress, is the basic point for selection. On the other hand, you can have a sliding seal where both elements continuously are into contact. Both have 100% of contact. A tribo system is a chemical reactor. You have operating conditions which goes into the contact, and at the end you can have a friction, wear, or a function coming out, and in between you have losses, especially heat by friction and also by wear particles. Coming now to the tribometry, you see here basically the bordered limits. A tribo contact in a tribometer or the test chamber, this is our border. We have two surfaces which come into contact. They are loaded, they receive normal force. Depending on the geometry and the elastic properties of the material, it results into an initial Hertzian contact stress. You have a sliding speed or velocity, either rolling, slip rolling, or sliding, can be unidirectional or oscillating. You have ambient temperature, a test duration. These are, let's say, the key parameters. The outcome is by means of a friction sensor of any time, the friction force You can measure the wear of both elements, of one element, by different techniques. Same for the temperature and also electrical properties like contact resistance, impedance, phase shift, permittivity, tangents delta, arcing, and so on. At the end of the test, you can use these specimens for surface analysis in order to see where the changes. At the end of the day, all those measurements today are electrical or digital ones. It goes into a data processing, into a computer, and at the end, during the test and at the end of the test, these results and properties are visualized and shown on a screen. In the near future, the next step would be that you have a curation of your data. You must check if the tests were valid, if you have to correct data, and at the end, the data will be archived in a data archiving system, which is more and more important in multinational companies who have globally different sites or labs operating different types of machines or on different sites. So the biggest point is longevity, and longevity means you have to measure wear. The situation for long is that different types of test equipment ask you to, or test procedures ask you to show or to report the wear scar diameter. You see on the left 3 wear scar diameter, and the blue shows you that the shape, even the diameter for all 3 is identical. The real abraded volume can be completely different. And here comes the first problem in tribometry. So imagine these 3 wear scar diameters were generated with 3 different oils. You report the same wear scar diameter. In consequence, you conclude all 3 oils have the same wear protection. But in reality, if you make by a stylus or by an optical microscope, you determine the real wear volume, you see there is a difference in wear volume, which is significantly, so all three lubricants don't offer the same wear protection. On the right side, you see a little bit what can happen. This is a trace with a stylus profilometer as the center of a wear scar. You have in a darker color, you have the initial shape, and the light blue shows you what in reality happened. It means you had in this case only the elastic deformation on the ball. The lubricant looped and protected very well. But if you look from top, you see a scar diameter because tribofilm on the surfaces were deposited, but in reality, wear is minimal. To give you some figures, in a test according to D6425, you have 2 different lubricants. One has a wear scar diameter of 0.478, the other one of 0.79. This is 1.65 times higher for the synthetic ester. But if you determine the wear volume, you have a difference of close to 23. This is why it is really better, but a little bit more complicated, that you determine on all specimens the wear volume, because you can much better discriminate or differentiate between additives, lubricants, and also materials. The only point is, because you measure here this the wear volume or the wear scar diameter at the test end, you get no information about running in unless you have a continuous measurement of the wear length during the test. There is another trend going to zero wear. Zero wear not means that the wear is zero, but you are at a resolution limit. And here the wear happens on the scale of microasperities. And it is clear by wear scar diameter and wear volume, this is hard to determine. And you need here other techniques who can measure the shape of microasperities before and after a test. So it is also here possible to determine wear, but on this level you have the problem. The changes in topography, were they done by plastic flow of the microasperity or really by an irreversible loss of materials? So finalizing, first takeaway here is if you only look on the wear scar diameter, it can be misleading, and one should look on the wear volume. To give you a range about the quantities you measure are shown here on the left side on a logarithmic scale for the friction, and on the right side for a linear scale for the friction. These were taken from a database with 19,000 test results. And the first point you see, also that's why you have so many different test equipments around, is that the wear rate goes over orders of magnitude, at least 7, 8 orders of magnitude. And it is clear that one test equipment can never cover such a large range in terms of wear rate or in terms of wear resistance. The same for the coefficient of friction. You have at least up to 2 orders of magnitude. And if you look on the actual research on super or supralubricity, so you go down to 10 times minus 3, and when you go, and if you consider rolling friction, you go down to 10 times minus 4 for the coefficient of friction. And this makes it a little bit complex and complicated from the metrological point of view to mimic all in one test equipment, which is nearly difficult to do or impossible. And this gives you an indication why you need so many different test equipment or test machines which can be adjusted for different load range. Those databases have also a very important capability, because when you now measure a material, a coating, a lubricant, and you get a wear and the friction result, is this good or bad? When you have such a database, you put the new results and you see exactly where you are sitting in comparison to all other past test results. How to come to the test conditions, or how to say if a test result is good or bad. The only way is to make a tribological system analysis. You have here this questionnaire, which is available in English, French, German. This questionnaire is published, and it asks you regarding your application some key informations, of course, the name of the tribo system you are looking for, the dimensions, the materials, the alloys, coatings, surface topography, what is the interfacial media, what do you have, dry friction, solid lubricant, and so on, the lubrication mode, the type of motion, the operating condition of your application, the contact stress. Do we talk about a geometric contact stress or about a Hertzian contact stress? The velocity, sliding speed, mean, max, average, same for temperature. duration, and so on. And you see, you generate here a quite big matrix of test conditions. That's why you also have this wide range of wear and friction. But if you want to have results which can be transferable to an application, you should have as best as possible the same conditions, including the materials in your tribological test equipment. The most widely used alloy in tribometry is ball bearing steel 50-100 or 100 CR6. But if you have special applications, you are in the situation that you really should consider to produce your specimen from such alloys you have in your application. The tribological characteristics are important in many ways because you must define what is the range of coefficient of friction you would like to have, what is the gap increase you can accept, and having this gap increase, you define when do you expect the loss of the function. And from this, you can calculate the wear volume, and with the other properties, you come to the wear rate. So if we go now back to these diagrams, you see a wide range of coefficient, a wide range of wear rates. So the question is not if test results anywhere is good or bad, but the point is, does the test results meet your tribological system analysis? It means if you have a wear rate which is allowable, all test results should be below. So by selecting results, it's not the question you are good or bad. The only question is, do you meet or do you not meet what you have analyzed by this question. And very important point in tribotesting is also the called overlap ratio. The overlap ratio, epsilon, is a ratio between the permanent contact area, in this case the red area of a flat pin, divided by the total contact area, which is the wear track on the disk. And also here you see one tribo element is in contact all the time, and a surface element on the rotating disk has some vacations during the test. And what happened, it's better shown here. You have the contact zone. In the contact zone, the tribofilm or the oxides or whatever may have been worn, they come out of the contact, and in this contact-free time, this can be regenerated, replenished, and it is logic. When you now increase the speed, you may come into a situation where you wear more of this tribofilm that it can rebuild. And this also explains why often you have an impact of the sliding speed on test results. At a certain point, you have a low wear, high wear transition. One outcome from the tribological system analysis is the so-called PV diagram. PV means a couple can afford a certain product, a certain combination of pressure, contact pressure times sliding speed, and we mean here not rolling speed, sliding speed in meter per second. So if you look into this schematic diagram, all lines you see or regions represent a transition border from mild wear or low wear to high or severe wear. It means even you have a very low speed, 0.01 meter per second, there is a maximum nominal contact pressure you cannot exceed, because the material begins to flow in the tribo contact. Even you have a very low contact stress and you go on the x-axis to high speed, 10 or 20 meter per second, even the contact stress is very low. You can also not exceed this sliding speed, because the microasperities may melt, evaporate, or creep. So you have two border limits which can be predicted, and in between you can exchange pressure and velocity. This means you not must exactly have the operating conditions in your application, but you must be sure that during your test you are in the mild rear region of the couple in respect to the application. When your load or your speed or your PV value in your test equipment is too high and you are under severe wear, you can never have results which can be transferred to an application. So important is to know these PV values of a material, of a couple, of a lubricant, and you must not have exactly the same PV value in your tribometer. You must at least be in the region of mild or low wear. But how you can now identify such a transition, such a critical contact stress? And you see here an example. It's a pin on disc test at 400 centigrade, 20 kilometers in hot steam. You have a point contact, and on the y-axis you see the total linear wear, which has a certain curve. But the wear volume not goes linearly, but it goes with the force power of the wear scar diameter, or the wear height, divided by the diameter of the bore. And then if you convert those curves, you see that at a certain point the wear rate is constant, and it means from this point onward you are in the low wear regime, because when you start such pin on disc test with a ball, you have at the beginning high contact stress, you get wear, the surface gets bigger and bigger, and the contact stress goes down automatically. It means when you have a linear wear measurement in a tribometer, you can distinguish if happens at this point, this critical contact stress where you have the low wear and high wear transition. Okay. Another important point, especially under dry friction, but even in some cases also under lubricated one, is relative humidity. At least under lubricated test, you should record the humidity. Under dry conditions, you must really control the humidity. You see here in an oscillating test under dry friction with ball bearing steel, you have the wear rate or wear coefficient as function of the relative humidity. And what you see that your results can be tailored by the humidity. And depending where you live, depending on the season, you can get different results. Here on the top right, you see also dry oscillation, two different materials for the stainless steels. Until 10–15% of humidity, friction is in this case independent, but when it gets dry, friction drops. This can also be embarrassing in application when you sell something into a very dry region. You have designed a frictional contact with a friction coefficient of 0.8, but in this dry region it drops down to 0.5. Or in the other case for ball bearing steels, when it gets humid, you have the drop in coefficient of friction. So not only to have constant and defined test conditions, you should at least measure the relative humidity, but also if you want to apply your results to an application, you should know the impact of humidity on your friction couple. Otherwise, you will have claims from customers saying it is not working, and other customers don't complain. And the reason was simple, that friction and wear depends from the humidity. Question of testing time. How do you come to the right testing time? This is not an easy question. Most pin on disk test methods have 1,000 meter of sliding distance, or 100 meter. 100 meter is certainly too short. And you see here's a problem. You have 3 evolutions in the wear. You have one evolution which goes straight. You have another one which starts slowly and accelerates. You have one with a high running in wear. You reach the critical contact stress, and then you come into a low wear regime. If now you would have had 19 kilometers of sliding distance as test time, you would conclude all 3 couples have the same wear resistance. But this is not true. If your testing time is too short, 1,000 or 2,000 meters, you would say couple number 3 is has an unacceptable high wear. We take couple 1, but this result is also not true. So I understand that everyone wants to have standardized tests, but this can be misleading in terms of selecting materials. You must be really sure that your test was long enough to be in a steady state, so you have the wear rate under the low wear regime, and no longer you are running in or into a high wear regime. So to find the right testing time, I prefer always to have longer testing time and to have more test machines than to have too short testing times, which can really mislead. Another problem is the mapping. If you look the range and variety of operating conditions, just to have one set of test conditions is not good to have a safe characterization of the functional profile of a tribo system. You see here two recent examples on mapping. It means that in these tests, a multitude of operating test conditions in a tribometer were used to get a 3D mapping of all relevant test conditions. The first point is, as you see, the test specimens are machined from real parts. This has the advantage that all unknown parameters which exist are in these parts, because these are production parts. When you produce a test specimen aside, they are in any case different from those from production parts, surface topography, residual stresses, many things. And this test here, you have this critical load carrying capacity for a piston ring cylinder liner as function of the liner temperature, as function of the load supply. And you must be sure that the test results are under all conditions above 50 newtons, to make really sure that under all operating conditions, this couple, including the lubricants, will not scuff. The same, maybe a little bit easier to understand, is on the right side, friction-induced noises of EPDM seal rings and brake fluids. The point is, when a brake fluid makes noise, then you get in your friction signal oscillations. And these oscillations are shown here in light blue. And the area of this surface is the quantity you report as sigma delta. So let's have a look. You see in these tests, you change the frequency, you change the normal force, and you test at different temperatures. What do you see now? The lower fluid, under any test conditions, you have low sigma values because the light blue surface is more or less non-existing. The red fluid, when the vehicle is cold, tends to make noise. And when the fluid heats up above 80 centigrade, you have no noise. The consequence is, if you would have, say, we test only at 80 centigrade, you conclude both fluids are good. But in reality, fluid number one makes noise when it is cold. This means customers goes to the garage claiming they have noises, but when in between from home to the garage, the brake fluid heats up, and now the dealer makes a tour with the cars and says there is no noise. We can't hear the noise. So mapping is really crucial in product certification and product development. And because tribometric tests are cheap, why not testing couples and lubricants and materials which are candidates for the application in a wide range of operating conditions? The electrification is, let's say, a new demand which comes onto fluids. We have today on the left side demands on reliability, life, against threading, frictional properties, oxidation resistance, corrosion protection. And now these fluids get new demands, additional demands on heat transfer, material compatibility, and electrical properties. The material compatibility comes from the situation that the fluids have now contact with much more different types of materials than previously. And the electrical properties come from the fact that they are, in most cases, generated by magnetic fields in electrical drives, not only in vehicles, but also in wind turbines. And these parasitic currents impact the tribofilm and can oxidize the lubricant, can have arcing and so on. This is quite a new demand, and for this we need tools. So when you run, let's say, as you see here, a mini traction machine test, and you record the impedance. Impedance automatically means it is an AC current over the frequency. Then you see during the test, when you increase the sliding speed, you come from same fluid, you come from a low resistance to a high resistance because you form a film, at least a hydrodynamic film. So you have already here the range from ohmic situations to capacitive situations. This also depends from temperature and from testing time, because on the rubbing surfaces, a tribofilm with completely different properties may be formed. If you make now a 4-ball test, you have a similar situation. So what you classic 4-ball test, 400 Newton, 1 hour of test, and you see here the coefficient, the evolution of the coefficient of friction, the evolution of the temperature or the friction torque, and you see here the contact resistance. For a long time during the test, nothing happens, and suddenly the contact resistance increases because a specific tribofilm is formed. And this is now really the debate if such a tribofilm formation is good or bad. At least for load carrying capacity and wear protection, it's certainly good. But in terms of electrical properties, the question is, when we have a build-up on electrical resistance on the surface, does it generate arcing and other properties which will degrade the lubricant. The crucial point with the electrical contact resistance or the electrical properties is shown here. You see two greases which are high performance greases. And now you make a fretting test according to D7594 at 50, 80, 120 centigrade. And you see here the electrical contact resistance is not the friction signal. Easily on the left side at 50 centigrade, you have a quite high electrical contact resistance, which at 80 and especially at 120 centigrade is very low. The other grease has at 50 and 80 centigrade a low contact resistance, but at 120, the contact resistance is high. And this can be embarrassing in the application depending on which temperature your application is running. In the right case, 50, 80 centigrade are good. You have no build-up, but at 120 centigrade, you have a tribo contact with a quite significant contact resistance. So this means you have not only to develop in future lubricants with low friction, very good wear protection, high load carrying capacity, but also to have the electrical properties being independent from the operating temperature. Here you see for the same greases the situation at 50 and 120 centigrade and plus the coefficient of friction. The coefficient of friction tells you in this case nothing. You see no change in the coefficient of friction, but in the electrical contact resistance. That's why we need to measure the electrical properties of tribo systems more and more in parallel, because over temperature these properties can change, and also, as you have seen, over time. So to finalize or to sum up, a tribological system analysis represents the basis in order to mimic the operating condition of a practical application in a tribometer. And the wide range of operating conditions, the wide range of types of motion require different test geometries, setups, and methodologies. You not must exactly meet the operating conditions by value. You must be at least in a range that you can be sure that you are, let's say, in the lower regime by means of temperature and PV values, and you should test sufficient long enough to be sure that you are not in the running in phase, which means always it's the high-wear region. The future challenge, we have overall electrified powertrains in vehicles, in wind turbines, and in other applications where you have DC and AC currents who coexist, and as well as inverter-induced bearing currents. The inverters in automotive vehicles run today at 12 to 15 kilohertz. Trends will be 20. In Formula One, you have 60 to 80 kilohertz, and in consequence, you have superimposed waves in the megahertz running in these systems. And this means all this must be mimicked in a tribometer. Second, we have different lubrication regimes in terms of a stribic type curves, and they can be modeled from under boundary and under boundary lubrication. We have the situation of an ohmic or of a resistor, and when the oil film develops, we come, due to the fluid gap, we come to a capacitive or to a capacitor. And second, the electrical properties of the total tribo system are composed of those from the tribofilm and those from the fluid, and they depend on top from the temperature. So we have now a multitude of quantities who came now on top into play: electrical contact resistance, DC, impedance, AC, relative permittivity, dielectric, the capacitance, phase shifts, tangents, delta, including arcing, where first we need those tools in our test equipment, and second, it is not fully clear what is good and bad for the application.
Okay, thank you very much, Matthias. A very comprehensive presentation indeed. So right now we will switch to our partners slide. So we have Philip Kemp from Artec Instruments, who will be giving a quick presentation right now.
Yeah, thank you very much for the nice presentation from Matthias Voigt and for the invitation from Sam and Surface Venture. So because we are short of time, I will go very quickly about Artec Instrument. We are a scientific instrument manufacturer for surface characterization, and we are in fact developing and selling mechanical and surface testing equipment that are in fact combining different techniques in order to give a very nice overview about characterization of materials and lubricant for a lot of different applications. The headquarters of Artec Instrument are in fact in San Jose, California, but they are really a worldwide presence, not only from Artec Instrument office in Europe and Asia, but also with a big number of sales channel and global partners that we have. In fact, we are having different kind of instruments for characterization of surface and lubricants, going from multifunction tribometer, but also some mechanical tester and 3D profilometer, including as well high pressure tribometer, rolling sliding tribometer, air jet erosion. So specific application in the field of tribology and mechanical testing. But what I would like to pinpoint today is more the focus on lubricant testing. It is true that we have some standalone instruments which are able to characterize lubricant and grease with a specific mode of testing, like SRV tester, 4-ball HFRR, or pin-on disc tribometer that was presented very nicely by Matthias Voigt as well in his presentation. But we have the unique modular platform of MFT 5000 multifunction tribometer that allows to characterize a very large range of application on this kind of platform. And with the universal platforms that we have, we can go from very small force to high force, from low speed to high speed, in order with a specific module of testing to characterize lubricant for a very specific application. It is true that on a multifunction tribometer, we have very dedicated option for lubricant testing that go from pin-on disc, 4-ball, and other oscillating linear mode of testing. And of course, there are specific accessory for lubricant testing, of course, the lubricant container, the accessory. And it's true that recently all the option of EC, electrical contact resistance and impedance measurements has been growing very, very strongly in all range of application. And we will release in the near future application note on the electrical contact measurements combined with lubricant testing. What is a unique option as well is a combination of 3D universal profilometer, including white light interferometry or confocal microscopy, in order to characterize the 3D deformation and specifically the wear volume on material, either one of the disc and the ball, in order to really have a complete overview of what would be the real wear on material. We can have really a very nice image about presence of particles, complete wear volume evaluation on the surface of the material. It is true that when we are going into lubricant testing, there are specific mode of testing that are generally related to ASTM and ISO standard. Pin on disc tribometer, which is sliding condition of ball on disc tribological tests, which are really well known in the field of tribology, but there are other testing methods extremely important for lubricant testing. Going from the SRV test method, HFRA test method for lubricity of diesel and fuel, the 4-ball testing, the mini traction machine, which has been growing interest in our application, also related to electrical contact resistance and impedance measurements, and for some application as well, the block-on-ring test. Just to give you a small overview, if you are not familiar, the fretting module is allowing to do SRV test, which is a high-frequency linear oscillation test. You have basically a ball which is in friction in a linear oscillating way, which is a standard method which is relatively well known and standardized. And with this kind of testing method, we have in reality a very dedicated instrument. The fretting module has a very specific feature in order to be able to do a very precise measurements on a linear oscillating way. We have a real-time normal force control with the applied force, which is well controlled with the software in order to have a precise measurements during the test. But as well, what is the key feature on this kind of instrumentation and design is a voice call with an electromagnetic actuator in order to have a linear oscillation with no bearings and no friction generated by the instrumentation itself. So if you are interested to have even more technical detail, we would be happy to explain you the real specificity of this kind of fretting test. We use, for example, a piezo sensor in order to be able to do high frequency tests and have a very precise and fast acquisition of what would be the coefficient of friction and the friction force of this kind of instrument. So in this kind of instrumentation, we are measuring the normal force, the friction force, the oscillation frequency, the amplitude, and then we determine what are the coefficient of friction and the linear wear of the material, and of course, a recording of different parameter and sensor like temperature or electrical contact measurement. So in fact, for the linear oscillation test that follows the SRV standard, they are in fact a very specific design in order to be able to provide very precise measurements and accurate measurements on a very large range of applications. So we are able then to measure the coefficient of friction on a repetitive way on this kind of SRV test, where generally the frequency is of 50 Hertz with a force of 200 or 300 Newton as an example. And it's very interesting to combine it with a confocal or white light interferometer microscope in order to, at the end of the test, evaluate what is the actual wear volume on the disc, but as well the wear volume on the ball. And all this combination gives you a very precise overview of what would be the precise estimation of what would be the properties of lubricant for specific application. The recent evolution about our instrumentation is also the mini traction machine, which is a specific setup that has been quite popular with EV testing and impedance measurements combined to tribology in lubricant testing. On our universal platform, we are able to install a lower rotary drive, which is doing a rotation from the bottom, but also a ball rotation on the top. So you have some pictures to explain you very quickly and very simply how it is operating. Is that basically you have a ball on the top with a load cell which is measuring what would be the applied force. You have the disc in a rotation, and a ball in rotation. So then we are able to control the sliding rolling ratio by controlling what would be the speed of rotation from the disc on the bottom and the speed of rotation of the ball on the top, as well having a load cell to measure what would be the friction force and the normal force applied. And then we have different load cells to measure the normal force and the friction force and the speed of rotation of the ball as well as of the ball of the disc on the bottom. What are the interest, in fact, to have this kind of option on a universal platform is that we're having X and Y motorized stage in order to control very precisely what is the radius of the testing, as well as the Z motorized stage to measure and apply very precisely the normal force. We have a very large range of flexibility with this kind of instrument, and it shows that we could go to higher load and higher pressure by just changing what would be the load cell on this kind of instrument. I will quickly finish on the 4-ball test, which is also an accessory on this kind of universal platform. We are installing, in fact, what would be an upper rotary drive, which is a rotation from the top. And it's following very precisely, in that case, the 4-ball testing by having the rotation of the ball on the top and the 3 balls that are on this bottom part. I have a long presentation, but I will go very quickly because of the short time. But if you are already familiar with the 4-ball test, this is done in a standard way, except the advantage of being able to control the normal force applied by an automated way. So it's very easy here to do testing at relatively high pressure, to follow the EP pressure standard test, or to do evaluation of the wear of the ball by doing other parameters. We can go from very high pressure to lower pressure, and also with some accessory of temperature heating in order to control the temperature and do testing at different temperature range, going from cooling to heating. So the big interest of this kind of automated software as well is the capability to automatically increase the pressure or the load in an automated way. So you can go from 100 Newton to 1,200 Newton step by step by doing automated increase of the pressure automatically with the software. And of course, you can combine it with a confocal microscope in order to precisely estimate what would be the wear volume on this kind of worn sample. There are, in fact, in reality, other method of testing with a block-on ring for grease and lubricant that I will not explain you today, and pin-on disc tribometer as well, which are a method of testing that we are providing with this kind of instrumentation. It is true that when combining lubricant testing with tribology, there are many requests of different geometry of testing, and then we would be very happy to discuss with you about your need and request of testing. The recent evolution in our tech instrument has been to combine all these kind of options with impedance measurements. And it shows that for the development of new fluid and electrical vehicle testing that has been requested very strongly for the past year. I thank you very much for your attention, and I thank Sam for the very nice organization of this surface event.
Thank you very much, Philippe. Right, so it's just looking at time, so I think we can spare a few minutes more to try and answer some of these questions. So, Matthias, can I just invite you back on stage? We can try and proceed through these questions. I'll now release the link for the attendance certificate. So for those of you that would like that certificate, please click on this. It will not be available after the event, but don't close the window yet. We'll stay on for a few more minutes. We have 4 questions. We're not going to take any further questions than that in the interest of time, but let's proceed with this. I hope that's okay with the both of you, that we overrun for a few minutes and just address these. Sure. Okay, wonderful. Let's begin with a question from Peter, who asks, what was the difference in the additive types and amounts between the two greases that you tested, Matthias?
Yes, I think it was stated in the slide.
I can bring the slides back up if that would be useful.
It is slide 19.
There we go.
Slide
19.
19. So we didn't make these greases. These are two greases from the DIN working group on grease testing. So one grease is a polypropylene glycol with lithium complex and EP and anti-wear, energy I2. This is all we know. We have all electrical properties I can share, and we have, because it was made public, and all tribological properties, 4-ball and all those stuff. And the second grade grease was a mineral oil with lithium and EP and energy I. This is all I know from the composition.
Got it. Thank you.
But I have some more details which were published within this working group. Yeah.
Okay. Got it. Thank you. Sorry. Okay, so proceeding on to the next question from Yanga. I hope I'm pronouncing that correctly. Probably not. Apologies. Is there a commercial tribometer especially designed for, I think this is meant to be current carrying friction? So perhaps a question for the both of you to answer.
I'm not sure if I correct this, if I understand this correctly, and maybe a translation issue. I understand this in the way that the gentleman or the lady is talking about arcing. Yes, it is available. That you can, when you make arcing, you have three options. You can keep the current constant, you can keep the voltage constant, or the contact resistance constant. Yes, this is existing. And if you go through literature, there you find a lot of literature now from institutes and companies who have done this in real ball bearings. And they use roughly 0.1 ampere per square millimeter of contact surface.
Yeah, in fact, there are different models of potential star and electrical contact resistance measurements that could be attached to tribological equipment. So sometimes it's not really a limitation in terms of the tribology equipment, but what are you installing on the equipment in order to do measurements? So there are some basic just electrical contact measurements, but there are also more advanced impedance measurements that could allow even more advanced analysis in tribology.
Okay. Excellent. Thank you both very much. Moving on to the next question, again from Peter, who asks, have you evaluated coatings on piston rings?
Yes, it's published. Same for Daimler and those, and also Götze, who use this Daimler test method. But the problem is, if you have specimens which are real piston rings, unfortunately, the real composition is not published. It's company know-how. There's a disadvantage of using real piston rings, and also you have then the shape and the geometry as it is in the application, which makes it a little bit more complicated to come to the wear volume. Yeah, because a production part is not so precisely manufactured than a certified test specimen.
Yeah, there is in fact a specific industry and option for piston ring cylinder lining and piston ring testing on coatings. I focus more my presentation on lubricant testing, but in reality there are some specific application on that. It is true that most of the automotive manufacturers which have this kind of equipment do not communicate about the measurement result they have on their coatings, because they keep it confidential, the result of their coating on piston rings.
Okay. Thank you. Right. Let's now proceed to the final question that we'll take today. I did see that there is one extra question in the chat, but unfortunately, in the interest of time, we'll just do this one and then wrap up. From Martin, who asks, thanks for this great talk. Do you have an idea how DLC-coated surfaces have an influence in E-tribology? They should be more insulating in general, right?
Yes, but they can be also doped with elements. What is a trend today to tailor the functional properties, and one consequence of doping is that you can steer the electrical conductance of the coating, and in this consequence you can avoid a charge build-up, because DLC coatings, when they are non-conductive, can store charges like an electret. On top, by doping, you also improve the absorption of additives. So doping is here a good solution, unless the dopant forms a carbide.
Okay. Brilliant. Thank you. Thank you very much for that detailed answer. Right. So I think now let us wrap up the webinar, as we're a little over time. But I would like to say thank you very much, Matthias, for your fantastic presentation. Thank you, Philippe, for your presentation as well.
Thank you, Sam, for the nice organization.
Of course. Thank you very much to Artec for the support for this event. As I've said and always say at the end of these, we would not be able to run our webinars without the support from our partners. So thank you. For those of you looking forward to the next Surface Ventures webinar, let me release the link for that now, with Professor Ivan Petrov of University of Illinois, a very well-known speaker in the field of surface engineering. You can register for that now. The link is on our website as well. Thank you very much to all of you in the audience for attending. Thanks for those great questions. And with that, just like to say, please do check out surfaceventures.org. You will see we have of course, our upcoming events. You can sign up to our newsletter, check out our upcoming events and posts on LinkedIn as well. And finally, we would just like to say, if you know anyone this would be of interest to, please do advertise these sessions to your contacts. It would be great to continue growing our audience. So with that, a final thank you all very much.
Thank you very much, Sam. Thank you, Matthias. Okay.
Thank you all. Goodbye.
Have a good day.
You too.